record and share screen with you. Okay, so Gibbs free energy is represented by this letter G. So delta G is changing Gibbs free energy. What we're going to talk about is there's really two ways to calculate it, two different equations, depending on the information you're given in the question. That tells you kind of which equation you use, okay? So what Gibbs free energy is kind of like it says up here, it's the energy associated with a chemical reaction that can be used to do work. So the energy associated with the chemical reaction that can be used to do work. And so one of the ways that we can calculate it was that we can actually use the change in enthalpy and the change in entropy. So you see the delta H and the delta S there. And then the temperature, which the temperature, like it says right here, has to be in Kelvin. The one thing you do want to be cautious of, though, is this delta S. Entropy, remember, has different units than enthalpy. Because if you remember, whenever I have enthalpy, delta H, that's always going to be kilojoules per mole. So it's kilojoules times mole to the -1. Well, when I have entropy, like we talked about last time, delta S is joules per Kelvin mole. So it's joules per Kelvin and then per mole. And so a lot of times not a lot of times, all the time, when you're using this equation, the delta S value, you're going to have to convert your joules to kilojoules. And that means that you're going to have to divide it by 1,000 before you can put it into this equation. And so we'll see that kind of on the example that we'll look at here in a second. But this kind of shows you that, like, depending on what numbers you get for enthalpy and entropy, that affects whether your free energy is going to be positive or negative. Because if, for example, if your delta H is really high, but maybe your delta S isn't, then that means your free energy, your delta G, is going to be positive. If it's the other way, if your delta H here is lower and your delta S is bigger, then you're going to get a negative value. And in order for something to be considered a spontaneous process, the delta G has to be negative. Okay, and so at the end, we're going to kind of talk about a summary about how all these things kind of fit together and how they affect each other. But let's go ahead and go through and do kind of an example here. So this one, it says we're calculating delta G, which is that Gibbs free energy, at 500 Kelvin. So they've given us the temperature here, and it's already in Kelvin, so we don't need to convert it. But the information they give us on the table, they give us enthalpy of formation values and they give us entropy values. Okay, so because those are the values they gave me, that tells me that I'm going to be using this equation, okay, with the delta H and the delta S and the temperature. Okay, so what I have to do is I have to solve for delta H and I have to solve for delta S, and then I plug both of those into this equation. So if you can remember, when we solve for delta H, we always do products minus reactants, okay? So for delta H, I would do, my products are CaO, which the delta H is this one, so negative 635. And then I'm going to add to it my other product, which is this carbon dioxide, so plus negative 394. And I didn't multiply either of them by anything because neither of them have any coefficients up here. So they're just one of each, okay? And then I subtract, and then my reactants, I only have one reactant, the CaCO3, and it's negative 1,207. And again, it doesn't need to be multiplied by anything because there's no coefficient in front of the CaCO3. So when I do this, I'm going to get the answer for delta H that I then plug into that equation to solve for delta G. So I haven't worked this one out on the calculator yet, so hold on. Negative 635 plus negative 394. So that is negative 1029 minus, and what happens when I subtract a negative? In math, when I subtract a negative number, what happens? You there? Time.
Wait, aren't you gonna change it to adding? Because
Yeah,
minus minus.
exactly.
So
Yeah.
add 1,
Yeah, because
2.
right here, since I'm subtracting this negative number, it turns to addition. So I'm actually adding 1207. Okay. Anytime I subtract a negative, it becomes positive. So I have negative 1029 plus 1207. So that gives me positive 178 for the delta H value. Okay. So now I got to do the same process for the entropy. So to get delta S, kind of the same thing. I do the products. So I have 39.7 and 214 for my two products. So 39.7 plus 214. And then I'm going to subtract my reactant, which that one is the 92.9. 92.9. So in this one, I'm going to scoot it up a little bit so you can see it. I have 39.7 plus 214, and then I'm subtracting 92.9. So for delta S, I get 160.8. Now, this is where when you go to plug it into the equation, I'm going to have to change this delta S value, the one I've written in red, because remember, this is joules per Kelvin mole. So this is what the units for that one look like. Whereas up here, this delta H, the 178, that one was kilojoules per mole. So I have to have them match. And so what I'm going to do is this one, I'm always going to have to divide it by 1,000. So anytime you do this equation, when you get the answer for delta S, automatically move the decimal 3 places to the left, because that's how you divide by 1,000. Anytime I divide by 1,000, that's what I do. So since I'm dividing by 1,000, this becomes 0.1608. And now it's kilojoules and then Kelvin mole. So now they both have kilojoules. So now I can use them in the equation. So just keep in mind, anytime you solve for the delta S and then you need to use it in this equation, you have to do this step right here where you divide by 1,000, because you have to convert those joules to kilojoules. So now that I have it converted, now I can go back up here, and now we're going to use this equation. Okay, we're going to plug in our values. So I have delta H minus the temperature in Kelvin times delta S. So I would do delta H, which was the 178, minus the temperature was 500 Kelvin, so minus 500 times this 0.1608. So I'm going to multiply 500 times 0.1608 and then do 178 minus that number. Let's see, 500 times 0.1608. So that's 80.4. When I multiply that, I get 80.4.
And you get 97.6 for the answer.
Oh, okay. Oh, okay. Yeah, you already subtract. Yep. So then when I subtract 97.6, okay, and then your units, like it says up here, is going to be your kilojoules per mole, okay, because the Kelvin canceled out from the temperature. So 97.6 kilojoules, and then it's mole to the -1. So The other way that you can solve for delta G is just like how we solve for delta H and delta S. You can do the products minus the reactants, but only if they give you the values for the Gibbs free energy for the equation. So if I come down here, these are some practice doing what we just did, but on this next one, okay, so here's how you would do it similar to what we did on the other ones for enthalpy and entropy. You add up all your products and then you add up all your reactants and you subtract them. So in this equation, or in this example, they gave me all of the values they gave me. These are all delta G of formation. Okay, they're Gibbs free energy of formation values. So if they gave me these delta G with the little f, that formation, that's where I would use this equation where I add up the products and reactants and then subtract them. Okay, so on this one, if I wanted to calculate delta G, I would do, so let's see, my products are going to be carbon dioxide and water are my products. So over here, I would start with negative 394, but it needs to be multiplied by, let me erase this and start over. So I have negative 394 times 2, okay, because there's a 2 in front of the CO2 in the equation. And then I'm going to add to that the other product, which is the water, which is negative 229. And that one gets multiplied by 3 because it has that 3 coefficient in front of the water on the product side. So those are my products. And then I'm going to subtract. And then on the reactant side, now if you notice here, oxygen is 0. Okay, most regular elements, they're going to be 0. They won't have a value. So that doesn't need to go in. I just need to use the value for this, this compound, which is ethanol. And that is negative 175. And it's not multiplied by anything because there's no coefficient in front of this one. So if I do my products, and I get negative 394 times 2, so that's negative 788 plus negative 229 times 3, negative 687. So if I add those together, I get negative 1,475. And then we said earlier, when I subtract a negative, that means I have to change it to addition. So since this is going to be subtracting negative 175, it just becomes plus 175. So 1475 negative plus 175. So this is negative 1,300 kilojoules per mole. Now, the other part of this question, if you read, not only do they want us to calculate it, but then it asks explain, or it says explain, state and explain if the reaction is spontaneous at this temperature. Okay, so we said up here all the way at the top of the first page that in order for a reaction to be spontaneous, the answer for delta G has to be negative. Okay, it's the second bullet right up here at the top. So is this one spontaneous or non-spontaneous? And how do I know that?
It's spontaneous because it's negative, right?
Exactly. So that's what you would, that's your explanation. You would state the reaction is spontaneous, you know, at 298 Kelvin, and your explanation would be because the value for delta G is negative, okay, which means it's spontaneous. So the last section really here just kind of puts all of these together. So we have delta H, delta S, and temperature and how they affect delta G and if the reaction is going to be spontaneous or non-spontaneous. And so we're going to talk about this and then we'll kind of look at a little chart at the very end. But first off, notice there's two sections. These are exothermic, Okay, down here underneath, there's endothermic. We'll get to that in a second. So exothermic, remember all exothermic reactions, all of their delta H's are negative. So if you look on the first section, delta H is negative for all these. It's less than 0. Okay. What changes is the delta S and the temperature. Okay. If I look at this one, delta H is negative, delta S is positive, meaning it's bigger than 0. So if that happens, if I have a negative delta H and a positive delta S, it doesn't matter what the temperature is. Any temperature, delta G will be negative, okay? And that means that, yes, it is spontaneous, okay? I'm gonna rewrite this a little bit. So I'm gonna put negative and then less than 0. On the other two situations, now delta S is negative on both of these. And so if that happens, if I have negative delta H and negative delta S, then it depends on the temperature, okay? With a high temperature, delta G will be positive, meaning it'll be greater than 0, and so this is not spontaneous. If delta G is negative, or I'm sorry, if the temperature is low, delta G will be negative, meaning less than 0, and then it would be spontaneous. So all of these little situations, you kind of just have to memorize which ones go with what, and then how it causes it to be spontaneous or not. The other section down here has endothermic. So on all of these, now if I look at my delta H values, they're all positive. Okay, so delta H is positive. So the first situation is positive delta H and negative delta S. Again, that means any temperature. The temperature doesn't matter in this situation. If that happens, then delta G will be positive. It doesn't matter the temperature, meaning it's greater than 0. So this is not spontaneous. The other situations are where we have positive delta H and positive delta S both. And in these situations, then this is where it depends on the temperature. A high temperature, it'll be negative, meaning less than 0. So that is, yes, it's spontaneous. If it's a low temperature, that's where I'm going to get positive Gibbs free energy, meaning greater than 0, and it's not spontaneous. So this can all be summarized on this little grid, this little chart on the next page. So think of this as like you're in math and you have like your X and Y axis, right? So on this, in this quadrant over here, okay, in this quadrant over here, this is where like your X value is positive and your Y value is positive, right? But if I'm over here, now X is negative, but Y is still positive, okay? Down here, X is positive, but Y is negative. And then in this last one over here, they're both negative. So X is negative and Y is negative. So we're kind of using that same concept. If you look, instead of X and Y, we have delta H and delta S, okay? So everywhere that I just wrote an X and a Y, I'm going to replace X with delta H, and I'm going to replace Y with delta S. I'm going to change the color too. So if I replace, you know, or wherever I had X and Y, I'm replacing it with delta H and delta S, because delta H is like the X axis, delta S is like the Y axis. So if your values fall somewhere in this quadrant, meaning that both of them are positive, okay, both delta H and delta S are positive, then that means it's spontaneous only at high temperatures. At low temperatures, it would not be spontaneous. If I go over here where now delta H is negative, but delta S is positive, that's this top left quadrant, that means it doesn't matter the temperature, it's always going to be spontaneous, okay? If I come down here and now I have my delta H is positive, but delta S is negative, this one, the temperature doesn't matter, but it's going to be non-spontaneous at any temperature. And then finally, the last one down here, where they're both negative, that means that it's only spontaneous at low temperatures. So at high temperatures, it would be non-spontaneous. So that this little grid kind of summarizes all the different possible combinations. And so, remember, positive delta H is endothermic, negative delta H is exothermic. And depending on which combination of these you get and the temperature, that's what determines if your delta G is positive or negative, which is what determines if your reaction is spontaneous or non-spontaneous, okay? And it can depend on the temperature as well, as we see on some of these. So that is pretty much it. Under here, you have some more practice questions over these topics to do.